Welcome to your podcast for Lesson 33, Inclined Planes and Friction. So after class, you should be able to solve for net force problems involving inclines and friction. So essentially, it's the same concepts that we were working with in the previous lesson, but now we are adding in that frictional force. So we'll do this project in class and do a couple example problems in class as well. Alright, some things to keep in mind. The force of friction always acts opposite of the direction of motion. So even if the object is not yet moving, whatever direction it's going to move, we know friction will act the opposite way. So for example 1, if you push on the side of a 5 kilogram block with a force of 10 newtons, the block remains at rest. Okay? What is the force of friction acting on the block? Well, the fact that it stays at rest tells us that F net is equal to 0. So what that tells me is that my force of friction has to be equal to my applied force, which in this case is 10 newtons. In example number 2, you're pushing on the side of a 5 kilogram block with a force of 10 newtons, causing the block to accelerate at a rate of 1 meter per second squared. And you are solving for the force of friction acting on the block. Well, if we apply what we've learned in the last couple lessons, we know that what causes this acceleration of 1 meter per second squared is the fact that there's now a net force acting on the block. And so we can say that F net is equal to ma, okay, mass times acceleration, and we also know that for that net force to occur, the applied force that I'm putting on that block has to be greater than that force of friction. And so we can write another equation for F net, taking the larger applied force and subtracting the frictional force. All right, when I set these two things equal to each other, I have ma is equal to the applied force minus the frictional force. And remember, I'm solving for my frictional force here. So when I rearrange, I get frictional force is equal to the applied force minus mass times acceleration, and now it's just a matter of plug and chug. That frictional force is equal to 10 newtons minus the quantity of my mass, which is 5 kilograms, times the acceleration, which is 1 meter per second squared. So 10 minus 5 is going to give me a frictional force of 5 newtons. Okay, now we're going to take that 5 kilogram block and it's going to be at rest on an inclined plane, but we know that angle is now going to be 30 degrees to the horizontal. So ultimately we're going to solve for the force of friction acting on that block. So the first thing that we'll do is to draw a picture of the incline in the block and all of the forces acting on it. Once we have that done, we'll split those forces up into their x and y components. And so we know that we have our new coordinate system on the block, and of the forces acting on this, we know that we have weight, which is acting straight down. We know that we have the normal force that acts perpendicular to that contact surface, and we can take our Fw and now split this into Fwx and also Fwy. Now this problem is bringing in friction. We know that friction always opposes motion, and so Fn is going to be equal and opposite still to Fwy, and so what's causing this block to move is its x component of weight. So it's going to slide down the ramp, but we know that friction is going to oppose that, and so we have our force of friction, which is acting up the ramp. Alright, so here's the same drawing. I just moved it up a little bit to show the work. So we've got our 30-degree angle here for the incline, and we know that that angle is always equal to the angle in between Fwy and Fw. And we also know, in this particular case, that our Fw we can calculate because it told us the mass of the block is 5 kilograms. So Fw is 5 kilograms times 10 meters per second squared, okay, or FW is equal to 50 newtons. We also know that this block is at rest. Okay? So since it's at rest, that tells me that my frictional force has to be equal in magnitude to my FWX because it's not moving down the incline. Okay? Now I know if I look at this triangle where I know this 30-degree angle, I know that this side of that triangle is equal to my FWX. Okay? And it's opposite of that 30-degree angle. So I can say that the sine of 30 is equal to the opposite side, FWX, okay, which again is equal to that. Okay. As opposite over hypotenuse, well, the hypotenuse is across from our right angle, so that's FW, and we know that is 50 newtons. So when I rearrange and solve for this, FWX is 50 newtons times the sine of 30, okay, or 50 times 1/2, which is going to give me a value of 25 newtons, okay, which we know is also equal, again, to our force of friction. Here we have a 2 kilogram block sliding down a plane that is inclined at an angle of 30 degrees. And this time we know, again, we have a friction force of 7 newtons acting on the block, and we are solving for the acceleration of this block. So again, the first thing that I'm going to do is draw my little coordinate system in here. Okay. And start drawing all the forces that are acting. And so I know on this block I'm going to have an FW, I'm going to have a normal force. I know that I have to take my force of weight and find its X component and also its Y component. The other thing I know, again, because this angle is 30 degrees down here, I know that this angle here is also 30 degrees. Okay. I know my force of friction is going to oppose motion, and since it's sliding down the plane, that tells me that my force of friction has to be acting in that opposite direction. So my free body diagram is going to look like this. Alright, we know that this block is going to accelerate, so acceleration is caused by a net force. So for this problem, I can write an equation for F net. In order for it to move down the block, we know that my FWX has to be bigger than my force of friction. So I can say that F net is FWX minus my frictional force. And I can calculate what my FWX is because I know that it is the same as this line down here, which is opposite of that 30-degree angle. Okay? So I can say that the sine of 30 is equal to my FWX divided by my FW. Okay? Now it's a 2 kilogram block, so that tells me FW, again, is equal to mg, or in this case 2 times 10. That's 20 newtons, so I can substitute that in. So I have 20 times the sine of 30 is equal to FWX. So 20 times 1/2 is 10 newtons for my FWX. So when I solve for my F net, I can plug in that 10 newtons minus my frictional force, which it told me was 7 newtons, which gives me an overall net force of 3 newtons. So that F net of 3 newtons is what causes my acceleration. Now I can plug that into A equals F net over M. Okay, and it's just a matter of plug and chug. 3 newtons divided by a mass of 2 kilograms, and that is going to give me 1.5 meters per second squared. Now again, remember, I can get meters per second squared because I know that 1 newton is equal to 1 kilogram times a meter per second squared. So if I'd plug this whole thing in on the top right here, the kilograms would cancel out, and it would leave me with just meters per second squared. Okay, this problem is similar. We have a force that's being applied to this 2 kilogram block, but now it's being pulled up that plane. So it's still inclined at 30 degrees, and I'm still going to start this problem by drawing my coordinate system on here. Okay. And I still know I have Fw, which is acting down. I still have my normal force, which is acting perpendicular to the contact surface. Okay. I still have to take my Fw and find its x and y components. Okay, there we go. But now I know that there's an applied force on this problem, and that applied force is pulling the block up the plane, and so I know my applied force has to be in that direction. Now, if it's moving up that plane, and we know the frictional force is 7 newtons, we know that force of friction is going to act down the plane because it's opposite of motion. Okay? So your free body diagram is going to end up looking like this. The other thing that we can add in, again, since we know that inclined plane is at an angle of 30 degrees, the angle between FWY and FW is also 30 degrees. Another key to this problem is seeing that it's moving at a constant speed. So remember, if something is moving at a constant speed, then there's no acceleration, and so F net has to be equal to 0. And so for this problem, what that tells me is that my applied force, okay, has to be equal to both my frictional force and my Fwx when they're added together. Okay, so I can solve for my Fwx. Okay, again, it's this side right here, which we know is equal to Fwx, and it's opposite of that 30-degree angle. So I'll do this over here to the side. The sine of 30 is equal to my Fwx over my Fw. Okay. Now we know Fw is equal to mg, and it's a 2 kilogram block again, so 2 times 10 is going to give us 20 newtons for my Fw. So when I rearrange this to solve for Fwx, I have 20 times the sine of 30, which is equal to Fwx, or 20 times 1/2, which is 10 newtons, okay, which is my Fwx. So I can come over here now and say that my applied force, which is what I'm solving for, is equal to my frictional force, which it told me is 7 newtons, plus my Fwx, which we've just calculated to be 10 newtons. And when I add those together, that's going to give me a total applied force of 17 newtons up the ramp.